Hey class, today we're going to talk about identifying linear functions. So for us with linear functions, we're going to focus on determining if it's linear on a graph, in an equation, and in a set of points or a table. But let's look at this first definition. With this first definition, we're going to say that a linear function Linear functions are algebraic equations whose graphs are straight lines with unique values for their slope and y-intercept. So a key word that we're going to really focus on throughout this actual lesson is straight lines. That's what we're determining based off the graphs, based off the tables, and based off the equations. Is that when we look at those, we've got to determine whether it's going to be a straight line every time. Okay, so if it is a straight line, linear function. Okay, if it's not a straight line, it's either a non-linear function or it's not a function at all. So as we move forward, we're going to start with our first one, which is graphs. So the graph represents a function because each domain value, which is your x value, is paired with exactly one range value for your y values. So what you're going to notice is that the graphs is a straight line. And a function whose graph forms a straight line is called a linear function. So when we look at all the graphs that are going to be given, and we have to determine whether it's a function or not, or a linear function or not, we're looking to see if it forms a straight line for it to be linear. Okay, so let's look at our first sets of examples. So the first example, it says which set of points form a linear function. So in order for us to determine this, the first thing we got to do is identify first, is it a function or not? And we can eliminate answer choices based off that. Then after we identify if it is a function, then we looking to form straight lines with the function that it is. Alright, so let's see. Answer choice A is a function. It would pass the vertical line test. Answer choice B is a function. Okay. So answer choice C is also a function, but if we look at answer choice D, that is not a function. Okay, so because it's not a function, we can go ahead and eliminate this answer choice. So that's already off the table. Okay, so the next one we're working with is A. Now we got to determine, because we already know it's a function, now we got to determine, is it linear? But see, they didn't really connect the dots for us this time. So because they didn't connect the dots, we're going to connect them from the farthest left, moving towards my right. And we notice that it's like a backwards check. And because it's a backwards check, it turned not a function. Well, not a linear function. Okay, so that's not our answer choice. Now let's look at B. Same concept. It did not connect the dots for us, so let's connect the dots ourselves. So when we connect those dots, well, we find out that it actually formed an upside down V. So this one here is not linear either. Okay, now looking at our last answer choice that was left, connect our dots. Here what we should notice is that it goes straight left and right. Because of that, this one is linear, and by it being linear, and we already know that it is a function, answer choice C will be the one that we have to select. Alright, so we're moving on to the next set. In our next set, we're moving on to tables and a list of ordered pairs. So you can identify a linear function by looking at the table or a list of ordered pairs. In a linear function, a constant change in the x corresponds with a constant change in my y. So what we're looking, if you look at the example, you'll notice how on my x side, every number increased by 1. And then I go and look at my actual y side, everything on this side decreased by 3. So what we should notice is that everything on this side is doing the same thing, everything on this side is doing the same thing, and because of that, they're changing at what we consider to be a constant rate. So that's what we're looking for it to be linear. It has to change at a constant rate on both sides. It can't be one number's different. They all have to be the same number, whether I'm dealing with my x or my y values. So let's look at some examples. Okay, so in order for us to determine whether it's a function in a linear function in a table, okay, we have to find the rate of change for the x and the y values. Okay, in order to do that, we need to put, especially the list, we have to list them in a table and find those rates of change. Okay, so let's do that. Let's start with answer choice A. We're going to make a t-chart with our x values on one side, y values on the other. So if I list my order pairs, we got -5, 0, -2, -2, we got 1, -4, and 3, -6. So what I mean by rate of change is this. What happened to -5 to become -2? So that was an increase of 3. What happened to -2 to become 1? That was an increase of 3. And from 1 to 3 was an increase of 2. Okay, automatically we see that on this side of our actual chart we got a change, but we ain't gonna count it out just yet. So let's check the other side. So we went from 0 to -2. That was a decrease of 2. Here what we have is -2 to -4. That's going to be a decrease of 2, and we went from -4 to -6 was a decrease of 2. So now that we have our changes, we're going to list them as a fraction. Remember, slope is written as m equals our y value, our y change over x change. That's going to be -2 over 3, -2 over 3, and then we got -2 over 2. So our list is not the same. So that means that is not a linear function. Okay, so let's move to B. Make our t-chart. In B we have -2, 3, -4, 5, -8, 7, and -16, 9. So we got to do that same process. So we got -2 change, -4 to -8 is going to be -4. From -8 to -16 is a decrease of 8. We went from 3 to 5 plus 2, 5 to 7 plus 2, and 7 to 9 was a plus 2. So we make our chart. We got 2 over -2. We got 2 over -4 and 2 over -8. They're not consistent. So because they're not consistent, that is not linear either. So let's move on to C. So when we list our order pairs for C, okay, let's find our change. From 2 to 1 was a decrease of 1. From +1 to -1 was a decrease of 2. And from -1 to -2 was a decrease of 1. So far on that side it's not the same, but don't count it out just yet. So from 5 to 6 was an increase of 1. 6 to 7 plus 1. 7 to 8 plus 1. So if we list them out, that's going to be 1 over -1. It'll be 1 over -2 and 1 over -1. That one in the middle is not consistent, so that's not linear either. So the last one is order pair, answer choice D. So we got 4, -5. We got 1, -3. We got -2, -1, and -5, 1. So we're going from 4 to 1. That was a decrease of 3. From 1 to negative 2, decrease of 3, from negative 2 to negative 5, decrease of 3. So far, this side, all are the same. Alright, let's check the other one. So we got negative 5 to negative 3, positive 2. Negative 3 to negative 1, plus 2. Negative 1 to positive 1, plus 2. So in our list, we got 2 over negative 3. We got 2 over negative 3. And 2 over negative 3. So all three of my changes match. So this one is our linear function, because they all match. Alright, so sometimes when it comes to these linear functions in a table, we might have to simplify. But if we don't have to simplify, we just got to make sure all three changes, or it could be more than just three, all of my changes match. Okay, whether we have to simplify or not, they have to match for it to be a linear function. So let's look. Another way that we can determine whether a function is linear is we're going to look at the equation. A function is linear if it is described by the linear equation. A linear equation is any equation that can be written in slope-intercept form shown on the right. So for us, slope-intercept form is y equals mx plus b, where m is the slope and y is called our y-intercept. Okay, if it fits that format, then it is a linear function. Okay, it has to fit that format. So to give you some hints about that format, it says that when a linear equation is written in slope-intercept form, the x and y both have an exponent of 1. So no exponent bigger than 1 should be attached to either variable. Okay, so the x and y should have an exponent of 1. Okay, it says x and y are not multiplied together. You cannot multiply. Okay, you cannot multiply those two together. X and y cannot be side by side for it to be a linear function. Okay, and then x and y does not appear in the denominator. It is not in the exponent, or it's not inside of a radical symbol. Okay, so I'm gonna give you a few examples of what it shouldn't look like. Okay, and then if it fits one of the ones that it shouldn't look like, then it's not linear. And if it don't fit the ones that it don't look like, it shouldn't be, it is linear. Okay, so let's look at a few examples. So if I'm looking at y equals x squared, remember the first hint says that x and y both should have exponents of 1. This is what we call an exponent of 2. So that means it's non-linear. Okay, when you have y equals 2 over x, it says that x and y cannot appear in the denominator, and x is in the denominator. Okay, so you might see something similar to that, where you also might see something like this. It says that x and y cannot be an exponent. Okay, so that's an example that you might see. Now the ones that I'm showing you, these are non-linear functions. That ain't what we're looking for. Okay, these are non-linear function examples. So another example will be, let's say we have a radical symbol with an x on the inside. You cannot have that symbol there. Okay, now this is just a few of them. Don't necessarily means that these are all the ones you could see, but this is similar. Okay, and it also says you cannot have x and y multiplied together. So you cannot have something similar, let's say, to this, or it will just show x and y. Okay, you cannot have x and y being multiplied together for it to be a linear function. But like I said, these are just examples of nonlinears. There are more, but we may come across some different ones, and we'll work through it as we get there. Okay, so let's look at the example set that we have for these. Which equation represents a linear function? Okay, so what we're going to do, we're going to point out and we're going to mark what you can't have. So in answer choice A, we're going to say no here. You cannot have exponents greater than 1. So that's a no-no. Alright, so answer choice B. Okay, I don't see anything that stands out like x and y being multiplied together and exponent greater than 1. I don't see the variable of x in the denominator or the variable x as an exponent. So we're going to leave that one alone for now. Looking at answer choice C, there's an exponent again, so this is a no because of that exponent. Okay, and answer choice D. Now answer choice D is a little different. It has parentheses, and you remember when we talked about parentheses, you have to distribute. So in some of these equations you might have to do some modifications to it, but if you modify it correctly, you'll know whether it's going to be right or wrong. So if I distribute that, that's going to give me x squared minus 2x plus 1. What we automatically should see, and that's going to be a no because of that exponent. So that's not a linear function. So the only one left is this one because it follows the format that we talked about. Y equals mx plus b, where m and b are numbers, they're constants, they can, and that's it. So the answer for this one is B, because this one is our linear function. Okay, so let's move to our next example. And our last example for this lesson, it says which equation is a linear function? Okay, so when we look at this one, looking at answer choice A, we got y equals 7. I don't see exponents. I don't see a variable in the denominator. I don't see anything out of the ordinary. So we're going to leave this one alone for now because I don't see anything weird about it. But let's look at B. B has parentheses. So parentheses means distribute. So if I distribute this one, we're going to get x squared minus 1x. And there it is again. There's that exponent. So this one's going to be a no because of that exponent. Okay. Let's look at C. Oh, there go an exponent bigger than 1. So here's a no again because of that exponent. We cannot have an exponent bigger than 1. And there's another one. Exponent bigger than 1. Okay. So in this set, the only thing that was kind of normal was y equals 7. So this one will be considered to be our linear function. Alright, ladies and gentlemen, so in this lesson, we figured out how to identify linear functions in graphs, tables, and with equations. So in graphs, we're looking to determine whether it is a function first and if it's a straight line. Okay. In tables, we have to determine if the rate of change is constant. Now, in tables, it's going to require the most work out of all three because you have to find the constant rate of change if it's available. Okay. And then in equations, it has to follow the format of y equals mx plus b, meaning it cannot have exponents. It cannot have the x as a denominator. Okay. It cannot have a radical symbol. Alright, that's just a few of them. But that's how we identify linear functions.